As she said, my name is Susan Mackay, and I am the CEO of Cerahelix. Cerahelix is the company that is commercializing the technology upon which my Moonshot is based. The way we produce energy in this country, both by traditional means and newly emerging means, can be very water and is very water intensive. So we use a lot of water to produce energy in this country. And you might say the most innovative energy technology that we're currently utilizing is in the oil and gas industry and the unconventional fuel extraction, which many people know by the name of fracking. And so in the area of unconventional fuel, they actually utilize a large amount of water and move a lot of water resources around to extract this fuel. And in fact, they use it a very low-tech way. If you've been in Pennsylvania in the last 10 years, you'll have noticed a growth of, in the middle of the woods, large highway systems where they literally have lines of trucks that are transporting water out of the state. And that's a very energy inefficient way to deal with water. So for this industry, over a 20-month period in 2011, the oil and gas unconventional fuel industry in the U.S. consumed 65 billion gallons of fresh water. And so the impact of that on our water system and on their own industry is driving that industry now to really look at ways to better reuse and recycle the water. And a lot of that is for many, the same reason anyone wants to reuse and recycle water is to do it in what they call a point of use. So actually to treat the water at the site of where it's being contaminated in a way that more cost effectively allows you to reuse that water. This both saves them money because they're now no longer using the energy or the costs of moving water around, which is a very inefficient way. So going back to the theme of the Moonshot, is fracking in many ways is to water technology startups like my own company. It's kind of like the space program of today. There's a lot of money and there's a huge engineering effort that's gone into building out this industry, and it's happened over a short period of time. And right now, they actually deal with more volume of water than they do with oil and gas. So the water that's produced on these sites is very highly contaminated. It's done at large volume, and it's a very expensive process and a very high, very sort of financially intensive industry. And so what you've seen is all the water technologies currently being developed, we're all looking at the same opportunity. There's opportunity in this oil and gas produced water space to develop our technologies and to prove them out in sort of this space age style phenomena where literally billions of gallons of water are being pumped down into the ground. They're being cycled through, coming back up along and having to be separated out in these very contaminated systems. And they're storing the water, they're trucking the water, they're treating the water. They've started just sort of using every water technology that was available, and they kludged together ways just to get the job done. And now as this industry is somewhat maturing within itself, they're finding more and more stresses as they're trying to expand, and they're just dealing with more water issues every day. And so for a company like ours to work in this space, it's a way to rapidly prove our technology and fund its development. So what they turned to first in this industry was really looking at what was the tried and true. If they were looking to get water to very high purity, and the reason for them to do this is that in order to reuse and recycle this water, it has to be close to fresh water composition. And that's because they use a chemistry package to do the fracking. So if they're going to recycle and reuse the water rather than just re-inject it in the ground, they need to get it to a high level of purity. When they tried to use more traditional high purity filtration membranes, they found that they fouled too much and they weren't rugged enough, and they were, in one case they told us they were replacing the filters every day. So they looked at materials that were more durable, like ceramic filters, and they work really well. They actually like ceramic filtration in this industry. But the problem is the ceramic filters that have been developed to date were really developed at not a high enough purity level. So the Cerahelix opportunity was to combine for the first time using a very durable material, creating a very high purity membrane that could be used to filter these types of highly contaminated water, and doing it in a very energy efficient way. So whereas before water and energy were optimized, technologies were optimized independent of each other, we for the first time developed this technology with an eye to making it truly energy efficient. So the way we did that is typically the way a ceramic filter is made is you take very small ceramic particles and you fuse them together, and the space between these particles is the pathway through which filtration occurs. So the smaller the particle size, the more fine the filter is. In the Cerahelix method, what we did is we take polymer in a different state, more amorphous ceramic polymer, so a ceramic material that's now more amorphous, and we incorporate DNA into this material. And we use a chemistry whereby the DNA is distributed throughout the material and is highly aligned within the ceramic. We then apply heat, after which both the DNA is removed and the ceramic material is hardened. And this creates straight aligned channels through the material, which provide a means for things to rapidly transport through the material and be filtered. And in fact, the pore size we were able to achieve, which is basically how small the holes are, it translates to how fine a filter it is, were significantly smaller than those which can be achieved in the more traditional ceramic processing method, where they're actually using ceramic nanoparticles and fusing them together. So even with what they called nanoceramics, there's still a much larger pore size, and so not as fine a filter as ours. And in fact, we avoid some of the issues that people are seeing with nanoparticle types of products, where we don't actually create a nanoparticle that then can become another issue. We're actually, for our nano piece of our technology, we're using DNA. So here's some electron micrographs, which are the very high resolution pictures of a cross section of our membrane. So underneath the very top layer, which is circled up there, is our actual membrane. So that's the material that we're creating, and it sits on top of the rest of the ceramic, which is sort of more in the ball shape that I showed before. And that's so once something can actually penetrate through our membrane, it rapidly travels through the rest of the filter and, is a very much faster process and way to do the filtration. So you can see in the more high resolution image on the right, our material looks, significantly different. So you can see sort of the physical differences between the type of ceramic material we're working with as opposed to the more traditional ceramic that looks more like a particle or a distinct particle. But even at this high resolution, you can't actually see the channels. So we back out that information to sort of characterize material by using indirect methods like absorption. So here is an absorption profile of the material with the DNA still incorporated. And then when we heat it up and remove the DNA, the smaller pores pop up, which sort of demonstrate what our pore size is. So it's less than a nanometer in terms of its size. So how does this fit into filtration? Well, more typically, filtration has always been developed to treat water. And so typically, ceramic filters have been optimized in what they call the ultrafiltration range, and that's where we really wanted to remove contaminants in water to make it drinking water quality. So things like viruses and bacteria that you typically just care about in order to create good drinking water. Sorry. With the Cerahelix technology, we've been able to take ceramic filters into a new regime. And that's where we're now actually targeting things that are dissolved in water. So with the Cerahelix technology, for the first time, we can remove organic materials or contaminants that are dissolved in the water that are much smaller than what you could filter out with other ceramic membranes. So here is just some preliminary data from where we actually targeted compounds of interest to the oil and gas industry. These are contaminants that they have trouble dealing with now. And they're each significant in that barium sulfate on the left, the blue bars is essentially the water that we treated, and then after filtering, the yellow is now the level. So we're in both cases with a single pass able to remove nearly 80% of the contaminant found in those water samples. And the significance of barium sulfate is when it comes up with the produced water, it also carries with it absorbed radium. And so you get a radioactive waste that's generated. And it also is a scaling compound. So when it's dissolved, if it doesn't get removed from the water, the dissolved component, and you try and reuse that water, it can actually impact the drilling equipment. So this is a high profile. Has a lot of high profile in the industry to try to deal with barium sulfate. Benzene as well is a volatile organic compound which is very carcinogenic and toxic. And it is another issue. It represents a class of materials that also cause problems when they try to reuse and recycle the water for fracking. So the fact that we optimize our technology in this space also provides a way then to take these same filters and apply them to other filtration areas and other industries and other end users who also want to remove these same types of compound from the water in order to reuse or recycle that water. Especially in the case of benzene. Benzene is one of those carcinogenic compounds. that for 2 million people in a Chinese city last April created a lot of problems, that they couldn't use their tap water because it became contaminated from the oil industry. And so, I think I said 2 million people. So in this one city in China, they've already dealt with issues of these contaminants. So it's not just people sitting in a fracking well that want to reuse their water. It's sort of everyone who lives more and more, as we're seeing more people live in urban areas, there's a drive to recycle and reuse water. And that kind of gets us back out to the big problem at the global level of how do we deal with our diminishing access to this fixed supply of fresh water. There's two technology ways available to us. We can try to create more fresh water, so you can take salt water and convert it to fresh water, or you can take the fresh water that we're currently using and polluting and treat that and reuse it and recycle it at the point of use. And right now, more and more people in the world are living in urban areas, and urban water recycling is 4 times more energy efficient than desalination. Plus, unless your urban center happens to be located at the coast, which many urban centers are, but not all, it becomes prohibitively more expensive, even once you've desalinated that water, to transport it to the point of where it's going to be used. And really, in urban water, the contamination is much greater. You tend to have more industry in those areas and more point sources of pollution, like, for instance, hospital water, where we're now seeing more and more dissolved drug residue and pharmaceutical residue. And there's a whole list of different types of contaminants, which are beyond what our earlier version of water treatment is capable of dealing with. So we're really looking, what the world really needs is new technologies that can now treat this water to the level needed to create clean, safe drinking water for everyone. So where are we in our development? At Cerahelix, we incorporated in 2011 specifically to commercialize this technology. We own the IP. We've developed all to date, everything within our own laboratory, solely sourced with federal grant money. So we have had more than $2 million in SBIR money go into our company to get to the point where we've taken the idea and we're now creating commercial scale filter tubes out using our process. So we're currently coating out in our laboratory meter-long filter tubes using our DNA ceramic technology. And these are what we're working with end users who are testing and validating our product in their laboratory and in specific sort of experiments, if you will, either in their lab or in ours, where they're trying to see how well we separate, how inexpensively we can actually, in terms of energy use and costs, treat the water to the level that they need. So we're benchmarking and validating with a series of different partners. So with that, I'd like to thank you for your attention.